Is this microphone on?
The microphone is...
I don't think so.
Yeah, I am picking it up, but is the sound system? So it's not transmitting to the audience?
I don't... Normally it would make a pop-up sound, right? It has a funny low battery sign, but I don't know if it's related.
Wait, does it have a low battery sign?
Yeah, low battery is blinking.
Oh, it is on low battery. How did that happen? Someone didn't charge it correctly.
I mean, do you think they're related or just...
I believe there should be spare batteries somewhere.
Is this a battery? No.
Oh yeah, these work as batteries, yeah. Try testing it. It's now full battery.
The microphone is not connected. In the worst case, I can get a microphone, a real microphone. Yeah, but
Yeah,
is there something that I'm not doing correctly? Is this supposed to be working automatically?
Yeah, it's supposed to be used like this, and it's supposed to feed to the sound system.
Well, is that microphone connected to the sound system? So your sound system is not on. It's not about these guys.
I think, yeah, it's probably the issue with the sound system.
Found it. There's a microphone volume knob here. Yeah. Thank you.
Yeah, someone had muted it.
Okay. Welcome, everyone. So after a little bit of diagnostics, I think my voice comes fine to the room. All good? Fine. It's a pleasure to finally be in the classroom. I think this is the 4th lecture. I'm Aydin Buluc. I'm co-teaching this class with Professor Yalak, you've seen in the first 3 lectures, and Professor Demel, you'll probably see him next week and the week after. So today I'm going to mostly be speaking about programming, how to program a shared memory machine. So it's going to be, these slides are actually from a tutorial, but this is not going to be a tutorial, so I won't give you time to actually sit down and implement them. You will not probably get all 100% of all the materials, but they will be there for you to go back and look at it if you need it during the homework and the project. So which is the goal. There is actually a tutorial like 3-hour planned presentation given by the lab at NERSC, And there's, if you go to the class website, in that master syllabus, I just added a link to it. It's going to happen in February 5, and there's also a link at the end of the slides for it. So if you want to learn more about it, it's going to be 3 times longer. I'm not going to say it's 3 times longer in the number of slides, but I'm going to spend an hour in OpenMP today, and they're going to spend 3 hours. That's what I mean. All right, let's start with a reminder on what is a parallel architecture. In general, essentially what we're talking about is it's a bunch of processors and a bunch of memory banks, and they're connected somehow. And what is this somehow is, subject to a lot of research, a lot of industry advances, and it keeps changing pretty much every 5 to 10 years at least. But that's not exactly important for the programming purposes. So I'll just go over a little bit about parallel languages before just going directly into OpenMP and try to tell you why actually we're talking about OpenMP. Before, when early in the 90s, there were these things called vector machines. Some of the old faculty will still have the posters from this machine called the connection machine. It's a very famous machine made by a company called Thinking Machines. Of course, like many companies, the many supercomputing companies of 1990s, they didn't survive, but that was a really cool idea. And the way that people programmed those things were relying heavily on the compilers. The compiler would actually find the parallelism and inform you very well if it can't. Like it will say, hey, you have this extra variable that is causing me not to be able to parallelize this loop. Can you please go back and fix that loop? That kind of feedback. And it actually probably still propagated into today's vectorizing compilers. When you go and get a vectorization report from your compilers, you can get the same kind of information if you insist on it. Like if you want more detail, there's a level of it, right? You can say vectorization report level 5, and it will tell you whether it vectorized that loop, and if it didn't, why it didn't. Then there's single instruction, multiple data machines. These are actually not particularly different, but it was really hard to do irregular computations. For both of them, mapping the same idea of using compiler-based parallelism onto clusters proved to be very hard. So even though people had a lot of hopes for this happening, it did not actually become practical. Then the shared memory processors, this has been originally programmed using POSIX threads. You might have learned it in your operating systems class, how p-threads run, how the synchronizations are happening. I'm going to go over them just for historical purposes and also to remind you some of the concepts, but you shouldn't be programming high-performance codes using POSIX threads, at least for this class, because it's particularly error-prone and there isn't a lot of performance benefits there. And OpenMP essentially is the most popular programming platform. You can call it an API. Some people call it a concurrency platform. And it's essentially making this creating threads and managing threads easy for you. You don't explicitly create threads. The OpenMP runtime will create the threads for you. And if it actually finds it more beneficial, it will not destruct the threads. It will just keep them alive so that it doesn't need to pay for the penalty of recreating it. So you delegate a lot of the low-level tasks to the OpenMP runtime. Of course, there was the cluster time. Essentially, we're not living any of these times anymore. I think the whole point I want to say on the slide is we're not really living in an era where there's only clusters that are dominant, or vector machines that are dominant, or shared memory processors. We have all of them today. And in fact, if you get an account on a supercomputer, anyone except NERSC, actually, you will get pretty much all of them, somewhat combined. What do I mean with that? It's going to be a big cluster, no matter what supercomputing you access. It's going to be some sort of cluster. So there'll be message passing that you need to do. We'll see that 2 to 3 weeks from today. And each one of the nodes will have a big shared memory CPU. So you'll have to be using OpenMP for that, at least for memory purposes. And then more often than not, they will have accelerators attached to it. So you'll have to be programming those, ideally with not another abstraction, but today we're still using things that are somewhat different from the rest, CUDA and OpenACC. There is an effort to bring OpenMP on the accelerator domain, and it probably needs a couple of more years for performance. The specification is there, the functionality is there, but the performance is lagging behind established things like CUDA and OpenACC. Anyway, and also if you look at accelerators today like GPUs, there are some sort of vector machines. They're just reincarnations of vector machines on a somewhat smaller scale. And then there's a cloud computing. So these are like probably a brief history of parallel languages. Today's outline, it's actually going to be a little different than that. I'll try to go over more than these 4 items in the OpenMP, and I'll try to focus much more on OpenMP than the previous years. So it's going to be a very different lecture if you've seen last year's version on YouTube or somewhere else. So what do I mean with shared memory model? So in shared memory, you can think of each processor having its own stack of local variables, and then there is a shared space. Every time you create a memory with malloc or new, usually things will go to a memory space called heap, which is shared across all threads. So every one of these threads will be able to access the memory that's created by malloc and new. And this is essentially how you achieve communication between threads. Right? You will basically write something to the shared memory, and it automatically becomes visible to all the other threads. And things you create in your own local stack, you create a thread, I'll go over that, and you create local variables inside that scope, those things will be invisible to the other threads. And OpenMP will make these things much more explicit, like what is private, what is shared. You will be able to annotate them and change some of these defaults if you want to change them. So this is the general thing. So start with threads. This is the old portable operating system interface, POSIX threads. This is, you're going to find it in any Linux, a POSIX thread, pthreads implementation. And this has lots of support for synchronization and creating threads and destroying them. And some of the concepts you've seen again in operating systems like mutual exclusion, semaphores, these are directly supported by the pthreads. And here's a little bit about syntax. I actually intentionally chose colors that are hard to see because you're not supposed to know these things. Everyone just looks at this and finds an example and modifies it. In particular, unless you have spent all your life writing C, there's not much benefit in making sense of that function pointer, which is a void star star star. Yes, you will be able to compile it and it will run, but really this is an artifact of the language. So anyway, that's the function. You're basically saying, hey, create me a thread with the function that I defined. So there'll be a function you define somewhere else. It will be usually called foo, but in this example, it's actually called thread_fun for function. So that's your standard C function, right? And what you're saying when you say pthread create is start a thread that runs this function. And the calling thread continues what it's doing, and you will pass the arguments in the last parameter to pthread create. So this is how you create a thread, and here's an example. There is a main thread. Of course, every process starts with a single thread of execution, and it goes into a loop, and it starts creating threads, six of them, and then each one of them will say hello world. And then after it's over, it will go and try to, actually 16 of them, not 6 of them, and each one of them will join. Join means just wait until that thread executes and reaches that location. So you will basically wait until all of them finishes. You see there's a lot of downsides of programming like this. One of them is you have to explicitly state how many threads are created, even though it might be more beneficial to write this hello world simply with less parallelism, right? So, but you have to say this beforehand, and this is an operating system call, which is expensive. That's also one downside. And And assume that these were like somewhat load imbalanced. Now think about this. This is not say hello, but some random function is running. And we don't know how expensive each one of these function calls are. So, but you have this funny joining in a loop. Assume that the first thread takes the longest time. But since you're joining the threads in an order of 1 to 16, even though the second, third, and the other threads have finished, everyone will first wait the first thread before the others can join. So, and there's no way to actually enforce these things in different orders. So this is the issue of the low-level programming with pre-threads. But anyway, this will run, and it will print hello world in a garbled way, because essentially there's no way to, with this example, you're not going to get the order hello words. They're going to be hellos, and words will be all flushed different times. So it's not going to be as nice to print it as you want. Okay, here, just to emphasize how bad it can get if you try to write p-threads based matrix multiplication. Is this what we're doing? No. We're just doing a small updates on a data structure, which is n by n array. So we're going to do something on each one of these n by n, each one of these cells inside this n by n array, and we want to do it in parallel. So we write two for loops, and within the innermost loop, you create a thread to update the cell. Fine. And I don't have the data about what the update cell function does, but it's not important. The point is, for each cell, you're creating a different function. So this will have to create n square threads, right? Even though n square might be too much, and you might not need that many threads. It might be much more beneficial to say, hey, create this thread only if there is enough work to do for the processors. You might have only 4 processors, right? But this will still create n square threads, and try to schedule n square threads on 4 processors, which will oversubscribe the processors. It's not necessary, but this way there's no way for p-threads to decide that this is too much and do less threads. It will create as many as you ask it. And then each one of these creations is very expensive because the operating system call. And unless your update cell is a very bulky function, you're not going to see a lot of performance gains from parallelism here. So those are the issues. Now, I think I've slammed p-threads enough, but it's important for concepts to understand that each one of these concurrency platforms, the one we'll see is OpenMP, is essentially creating some sort of threads on the background. It might not create the threads for every loop. It will create the threads once, and it will manage the thread pool later so that it doesn't pay the cost of creating them. And it will make it easy for you to do these things of, hey, there's way too many threads you're trying to create, but you have only 4 processors. I'm just going to create 4 of them and divide the loop space in a better way. And we'll see how that happens. Okay, the next thing you have to understand when you're programming is something called a data race. A data race happens when 2 threads, at least 2 threads, are accessing the same memory location, and one of them is doing a write operation. That's all. If both of them are reading that memory location, there's no data race. But at least one of them is doing write. There's a race condition, and it means that depending on the run, you might get a different answer. Sometimes you might actually get garbage depending on what you're updating. If it's not a single word on the machine, if you're updating a bigger data structure, it is possible that half of it will be updated, and at that point the operating system will switch to the other thread, and then it will see the data half updated, so it's going to be garbage. Like, think about updating a big complex number, which is not represented by a single word. So it might be that the imaginary pipe will be updated, and the operating system will yield that thread, and the next thread will see a number that is half updated, the other half is still garbage. So those things are possible. There is a group of people that think that there's benign data races, which means the data race is not a problem. It is something part of the algorithm. And there's another group of people that says there's no such thing. Every data race is harmful. And I'm not going to go into those details. There's lots of papers about those if you're into that kind of research. Mutex. What is a mutex? A mutex is really a way to say that I want this part of the code to be accessed by only one thread at a time. Okay, mutual exclusion. That's the short, mutex is the shorthand for that. So you basically acquire a lock in this case, and at that point, any short snippet between the lock and unlock will only be executed by one thread at a time. So that's one way to achieve synchronization, avoid the data races that we talked about. So what's the problem with this approach? Did anyone use locks ever in their codes? Yeah. Did you see any problems with that, or just work fine?
It makes code really messy, and if you forget to unlock in one place, it's going to unlock.
Yeah, there's the potential of deadlocks. The deadlocks are somewhat easy to recognize by tools, but it's still, for you, by staring at them, it's not easy. And the second one is if you use them a lot, it's going to destroy all your performance benefits from parallelism, because essentially you're serializing that piece of the code, right? And only one thread, everything else waits there. And this is the syntax of how to lock, how to unlock, how to initialize the lock, how to destroy the lock. Lots of things that you have to take care of that OpenMP will do for you. You won't need to worry about them. But, so just an example, what's happening at the deadlock, just to verify, let's say the thread 1 is calling lock A and lock B, trying to access two different locks in this order, and the thread 2 is trying to access them in a different order. Well, of course, thread 1 controls lock A, waiting for lock B, thread 2 is controlling lock B, waiting for lock A. They will stay in this position forever. The simplest way to fix these kind of issues, if you really want to use locks, is to make sure that the threads access them in the same order. But that might not always be possible. Your application might require something different. But if you make sure that every thread accesses all the resources in the same order, you won't see deadlocks. Summary, P2X are operating system features. They're expensive, but they're portable in the sense that they can be used from many different languages. You can actually use that to synchronize between threads. It's essentially, if you're not writing performance critical code, but instead if you're writing some code that tries to access a shared resource, shared file, they're appropriate. The downsides I already talked about: overhead, data races, and OpenMP is usually the way people program when they want performance. So we're going to go over that. So what is OpenMP? One, as I said, concurrency platform is the word I like to use, but people call it just an application programming interface, API, to write parallel software. This is a long history. It is supported by C, C++, and Fortran, at least, officially. There are bindings for those. I believe C++ is no different than C. So what does it allow you to do? It will automatically handle the thread creation. It will make the synchronization easy for you. Some of the management of the memory will be default automatic. You won't need to worry about it unless you want OpenMP to do something different from the defaults. But it will not automatically parallelize your code. That's your job still. It will not guarantee your speed up, and we will see examples on why things don't speed up as much as they should, even with simple cases. And hopefully in your homeworks and your projects, we will avoid them. And it will not guarantee data race-free execution. One of the reasons OpenMP is a little disliked by the academic community is the bloat that happens. OpenMP started as something really simple, and it only wanted scientific programmers to accelerate their loop-based codes. Computational chemistry code, computational physics codes, they're mostly expensive, floating point heavy loops. So it started with how to parallelize these loops efficiently. And then as years has passed, these are versions of OpenMP that are tagged on top of these circles and squares and triangles. So, I mean, there's a reason why they're different, right? One of them is there was a separate Fortran and C++ spec, and they got merged at some point. That's why there's 3 different geometric objects. But the more important point on the slide is the number of lines, number of pages on the spec has been going up pretty steeply. And we'll see why this is the case. Some people wanted more than loops, they got it. Some people want different semantics, they got it. pretty much a lot of people got what they wanted. And then towards here, now you can actually program accelerators like GPUs with OpenMP, and understandably, the number of lines keeps going up. That might be a little intimidating for someone that tries to go into OpenMP initially, and hence the benefits of this class. Most programmers will only use this table. It's something I'm happy to say, but I'm also a little worried, because when I started as a grad student 10 years ago, somebody, the teacher showed me a slide that says pretty much all the functions you need in MPI is in this slide. And I pretty much don't use any of those anymore. I use a completely different set. Take this with a grain of salt. But if you need a cheat sheet, you can come back to the slides still, nevertheless. As you learn more, you'll get out of this single slide. Has anyone used OpenMP already? Okay. Successfully, unsuccessfully, what is your somewhat? Good? Okay. All right, so it has at least 3.5 stars on Yelp. I think that's what it looks like. This is what OpenMP stack looks like, and I don't know why this would be important for you, so I'm going to skip this. And this is the basic syntax. Pretty much all the to convert your code to an OpenMP code, one of the first things you do, you add a header file called omp.h. Then you will use a library flag. I'll show it in the next slides or so. And the majority of these things are on the syntax that starts with this sharp. What was that sign called? Yeah, the pragma, OMP, parallel, whatever. But the construct, in general, the syntax is pragma, OMP, something, okay? And if you, most of those things will be ignored if you don't compile it with the OpenMP flag. So your code will be a successful serial code in general, except for a few direct OpenMP calls like give me the number of active threads or give me my thread number. Those you will need to protect with some sort of if-def OpenMP, use this function. If not, you call that function. Otherwise, all of these pragmas will be ignored. So that's kind of nice, because you can then test your serial code for correctness without worrying about parallelism. And once you make sure that your serial code is correct, then you can deal with all the bugs you introduced by using parallelism. Here's a hello world again. This is how you would print hello world as many times as there are threads in the system. Okay, so you added the header file, you added the parallel. So unless you write parallel, nothing is parallel in OpenMP. So to start parallelism, you basically put this pragma OMP parallel. Good. And the scope within this thing, like the open bracket, close bracket, within that scope, the code will run in every thread. How many threads are there? That's actually a good question. In general, based on the runtime, most sane OpenMP implementations will look at the number of cores, including the virtual cores, meaning that if you have hyperthreading, and in your 2-core laptop, it will say 4 as a default, usually. You can change that multiple ways. You can change it by changing the environmental variable called OMP numthreads. Before you run the code, you export OMP numthreads equals 2, and it will run on 2. Or you can change it inside the code. And I might have a slide on that or not. But essentially, all that's doing when you call those functions is there's an internal number the library is keeping track of how many threads I should be using at most. And it reads this every time it starts a loop. And it will never create more than that many threads, but it might create less than that if it thinks that there's not enough work in your construct, it's not worth doing it. In this case, it doesn't have a choice. You're basically saying, run this code in parallel for as many threads as there are. It cannot create less than the number of threads, because it's a correctness issue. But we'll see when in this called work sharing constructs, the compiler has the privilege to decide how many threads it will create. And you'll see what I mean. Anyway, this is how you would call this, compile this. This is the flag. Of course, you'll put the other flags too, the optimization flags. But the additional flag you will use this usually is fopenmp or something else. All right. Of course, this is the standard garbled output, because there's no way to ensure that they're ordered correctly. And what's happening is a good conceptual diagram of what's happening is main thread starts, which is the red line, right? And it goes into a parallel region. It forks multiple threads, as many as there are threads, including itself. The main thread is one of those threads. Remember, that's why it's shown the red line continues, and then it will finish that parallel region. It will join, the so-called join, meaning there will be another time there's only one active thread until the next parallel region. And what is possible, maybe this figure doesn't show, is you can nest these things, meaning that within a parallel region you can have another parallel region. That's fine. So then the fork join will be a little nested. Okay. Oh, here's the nested example. Wonderful, right? Thread creation. So, okay, I did have a slide for that. You control the number of threads if you want to control them this way. If you want to let the operating system use as many cores or threads it thinks, that you don't need to set this. But if you want to control how many will print hello world, you can do it this way. Set num threads and it will change the internal variable. So what is it going to do? Inside the parallel region, each thread will ask the OpenMP runtime, what's my thread ID? And that function is OMP get thread num, and then it will call a function with that ID and the shared variable. So what is A? Which one of the threads can access A? This variable outside the parallel region. Any guesses?
All of them?
All of them, because it's outside the loop. By default, things that are declared before the parallel region are shared across threads. All of them can access them. And the ID can only be accessed by the thread that's running here, because that's a stack variable inside the scope. That's about it. Okay? So that's simple, but that doesn't look that useful so far, right? We'll get to useful stuff. Okay, so this code is executing redundantly. This is very similar to the concept that you'll see in MPI. Basically, this is called SPMD, single program, multiple data. There's a single program running redundantly on each one of these threads. Right? The same code is running. Whatever the code is inside that lexical scope, it's running in every single thread. So and then once that scope is over, there is an implicit barrier, meaning that all the threads must end before the execution continues. Before the printf all done can be printed, all the threads should be done. And that's true for pretty much all work sharing constructs. All the parallel regions have an implicit barrier. We'll get to that later again. So how many threads did you get? I talked all of this so far. There is an internal number by default by the implementation. You can change it two ways. I said set num threads is one way, and setting the environmental variable is another way. And cool, here's the example. I think this is the best way to learn, otherwise it becomes too abstract. The reason this pi example is nice is because it's going to be used in MPI as well, so you're going to see the same example. So how do you know from the calculus that one way to integrate is to use these little rectangles, right? You make the rectangles width small and you get a better approximation. And it turns out the pi, there's an integral formula for pi. If you integrate between 0 and 1, this nice formula, you'll approximate pi. Great. You don't need to worry about what it is and why that's correct. But the computer implementation of that is, I'm going to choose a delta, whatever the x, I'm gonna take it as small as I want, if I want a good approximation, and I will sum over all the values of f. And what am I going to use as the f? And I'm going to use the middle. I can use the left, I can use the right, doesn't matter. So I'm going to use the mid-range of this rectangle, and here becomes the code. So I take a bunch of steps between 0 and 1, and I decide how many little rectangles I'll do by the number of steps. And then I decide on the step length based on the number of steps I decide to take. And I just run a loop. It will choose an x, which is the middle of that rectangle, find the function value at that, which is this formula that was there, 4 over 1 plus x squared, add it to the sum, and do the next rectangle, add it to the sum, next rectangle. But this is correct. So how can we parallelize this? What is the computation is happening inside this loop, right? Everything else is kind of setting the variables. Most of the bulk of the computation is happening inside this for loop. Is everyone clear with this example? Okay. Fine. So before I get parallelism, I want to find out how long this takes in a serial code. And OpenMP allows you to get the time, even though there's no OpenMP constructs here. If you compile it with OMP-H, you'll be able to use this OMP get wall time, and W is wall. Again, this is copied from MPI. MPI W time is the name, and so we're gonna use the same in terms of name, which is good. It's gonna make you remember it. And how do you parallelize this thing? So the first attempt is rather simple. I could have let you do that if this was a tutorial, but what you do here is, okay, I'm gonna create an array. Okay, so instead of having one sum variable, I'm gonna have an array called sum, and it will have length number of threads. Right? So if there are 4 threads, this array will have 4 elements, and every thread will accumulate its own local piece of that array, which is some ID. It's going to check its ID. What's my thread ID? Okay, fine. And then I'm going to accumulate my sum into that location of the array. Because if it tries to accumulate to the sum, there's a data race, right? Remember, if everyone within that parallel region tries to update sum, you have a data race, and you'll get garbage. To avoid the garbage, what you do is everyone writes to its own independent part of this slightly longer array. And then once this parallel region is over, you go and run a very short loop for a number of threads and just, sum the entries in the sum array, and that will be your pi. That's that. Does it make sense? The reason this looks a little funky like it's old Sega computers is I tried to shrink it by taking a photo, and it was taking too much time, too much space on the slide. And if you run this code, you'll see this performance. The single thread version will run in 1.86. The second 2-thread version will run that much. Well, okay, what do you see? What might be an issue here? Just forget about the code. Does this look like good scaling?
No, the margin is decreasing.
Yeah, this is not this is a fairly easy to parallelize code. Why? Because it does a lot of computation. It doesn't do a lot of data access. So it's not, limited by the access to the DRAM. So it should parallelize very well and should get really good performance. Instead, with 4 threads, I'm seeing less than 2 times speed up. That's a little problematic. What might be the reason? Just to motivate you a little further, I've been asked this question once on an interview. Okay, so long time ago, but. So to explain that, I'm going to create a parenthesis here and talk a little bit about memory. Remember, I said parallel computers are like this. There's a bunch of processors, there's memory, and there's interconnect in between. But that doesn't explain everything. There's something called a cache, right? Every one of you might have heard the concept of L1 cache, L2 cache. If you haven't, these are the faster memory that is very close to the cores. And usually L1 cache is private to each core. L2 cache is technically shared between several cores, but that doesn't matter. That's like for you to avoid the whole trip back and forth to the DRAM. If there's an item that's frequently used, it's kept in the cache. Okay? That greatly makes the certain codes go significantly faster. And so every modern processor has deep memory hierarchies with lots of caches, levels of caches. Okay, well that's great. So caches are good, but how do you keep caches coherent? That's the problem for computer architects. And here's an example. So the numbers on the arrows tell you the order of the things that are happening. So first, there is an element called u. There is a variable called u. It's in the memory, main memory. Its value is 5. processor 1 reads that value, and once it reads, the cache decides that, hey, maybe I'll need this later. I'll keep this in memory, in my cache, local cache. Fine. And then processor 3 wants to read U, okay, and the cache decides to keep it in case it's required, there's another access to it. But then processor 3, after reading, updates the value, 7. Good, so now there's this variable U in 2 different processors' caches. One of them has a value 7, the other one has a value 5. That's a little problematic, right? And the thing called sequential consistency would require that that value, if after this point, P1 makes a read, it should read 7 if these things are properly sequentially consistent. How do you ensure that? Well, there's lots of, so basically, there's lots of protocols that I'm not gonna talk a lot about, but one of the fundamentally what it turns out into is called the coherence protocol, right? Every time you basically are updating a value of interest that's somewhat shared between, you know that this value exists in more than one processor's cache. Every time you make an update, you try to propagate that to the other cache lines. So that's basically most of the protocols are doing. There are names for these. Here's one example just for you. If you're interested, you can read this thing. It's called Snoopy Cache Coherence Protocol. Like basically, the cache controller looks at the bus, the communication medium, the interconnect between processors, and if there's a relevant transaction that includes a variable in one of the caches, and it sees an update on it, it tries to snoop that and propagate it to other caches. That's the protocol. Okay, so this looks like a little too much for you to know, right? I mean, what does it have to do with this example that we talked about? Any guesses?
Is the U or the array like written all the caches?
Yeah, so the problem, great answer. I'm just gonna skip the sequential consistency thing. Okay, this is what the caches look like, thank you, is it's designed as blocks, so-called cache lines, right? It's not one word at a time. Transactions between memory and cache happen in blocks. Usually it's 128 bytes or something like that, so that there's not a lot of, like for each byte you don't go to the cache to update it. So the whole 128 or 64 or whatever, depending on your processors, gets copied to the memory altogether. Good. Well, what does that mean? The chances are this sum array are in the same cache line. Like the sum, the zeroth entry of the sum is here, the first entry is here, second, third. Okay, wonderful. Which means the whole array is, if there's few threads, are sitting in the same cache line. So thread 1 is updating its own part of sum 0, and thread 2 is updating sum 1. Good. But they're all in the same cache line. Every time there's an update, cache coherence protocol says, look, there's an update in the sum. I have to, is there any other processor that keeps this variable in its cache? Every single processor has the same variable in its cache, because it's frequently updated. Then it says, okay, I have to propagate these new entries. Like, this is unnecessary. This is why it's called false sharing, because actually these variables are not shared. They don't need to be updated, because one of them is updating only sum 0, the other one is only updating sum 1. Unfortunately, the reason these things are created as lines or blocks, that stops the hardware to know that they're separate things. So every time you update sum, extra coherence traffic happens under the covers. That's what's stopping you to scale. And if Jim was here, he would tell me to say, don't use your hands, use your mouse, because nobody will be able to see it in the YouTube video later. So I'll stick to that. Examples, how to fix this. The simple and ugly way to fix it is to look at your cache line size. Okay, so what is it? Let's say it says 128. And then you think about it. Okay, what is the double? Double is 8. Right, so if I add a pad padding vectors of length 128, let's say, 128 bytes. What would it be in doubles? It would be 16 doubles, right? So if I add pad to be 16, now this example is assuming 64-byte cache line size. Sorry, let's stick to this example. Let's not worry about 128. Then you would add padding of this array. So what would it change? The array, as a 2D array is laid down the memory, it will be like the sum's first entry and the sum's second entry will be 8 doubles apart, which means they will not be in the same cache line. Done. You're kind of redundantly creating empty space, but for a small number of threads, that's okay. And there will not be any false sharing. It's ugly, it works. But we'll give you a better way to deal with this mess. So what do we see? We see almost 4 times speed up. Maybe not quite, but 3 times 7 speed up on 4 threads, which is what you would want to achieve. So things are not that bad now after I added the threading. Sorry, the padding. Any questions? Good. This is, I think, an important concept. So synchronization, critical barrier. I'm going to show you how to do this in a different way. For the jargon, one of the bad things about OpenMP is lots of jargon, and one of the nice things about this class, this lecture, is I'm telling you the jargon so that you don't get intimidated when you read the spec or the websites that talk about the functions. So there's essentially 2 major classes of constructs in OpenMP. One of them is so-called work sharing construct, the other one is called synchronization constructs. And just to complete the jargon, so this concept called critical is a synchronization construct. You can think of critical is an easy way to achieve mutual exclusion, like the locks you've seen in pthreads half an hour ago. This is going to achieve the same thing. What will critical do is only one thread will be active within that region at a given time. That doesn't mean that section will be executed only once. It will still be executed as many times as there are threads. But the accesses, the execution will be serialized. The first worker will go, first thread will go, execute, let's say, and then the 4th thread will execute, and then the 2nd and 3rd. You don't know the order. But in some order, they will execute this in a serialized fashion. They will not be executing the code at the same time. So that's what the critical achieves. And you can put this critical inside your parallel region, and it will serialize only that piece right under it. Or if you put a block, that's fine. So, and the second synchronization construct that's important to remember is a barrier. And what does a barrier do? A barrier says, until all the threads reach this line called barriers, do not go past beyond this point. Okay? Is that clear? Actually, the name is really nice, barrier. Until everyone reaches the barriers, do not execute anything under it. It doesn't talk about anything about memory. That's a different operation. It just talks about the execution. The code above should execute. It doesn't say that those changes in the variable should be visible to other threads. That's a more expensive operation called flush. We'll see maybe later if we have time. Okay, let's rewrite the pi using critical. So what did we do now? So notice that instead of having a sum that's shared, I created a sum per thread because I defined the sum variable inside my parallel region, which makes it local to the thread and invisible to all the other threads. It's a stack variable, so everyone updates the sum. The thing is, I cannot close the parallel region here and then try to merge the sum values because the sum is going to disappear. It's going to go out of scope, and it's going to be destructed. So I have to use those sum values, the independent private sum values, before I exit the parallel region. And how do I do that? I go into this critical section, right? Say, only in this part of the code, things are serialized. First, one thread adds its sum to the pi, then some other thread adds it. So there is no data erases here, and the performance will be okay. And the reason why is because the computational intensive loop is here, and that doesn't have a critical section. if I was stupid and I put my critical statement inside this compute-intensive loop, the chances are I would see very poor scaling. But since I did the bulk of my computation without a critical section in there, and I only do critical for a very short loop, it's not even a loop, but this is something that's executed by threads, 8 of them, 16 of them, very few threads, that's okay. And as you can see, it's just as good as padding. In fact, you know, there is a measurement error, little margin difference, but it achieves just about the same performance. Any questions? I mean, it's not that hard, but actually it's going to get even easier coding-wise. So here's something called work sharing construct. The way we so far defined, so far the only way we worked is, hey, we define a parallel region, the code block within the parallel region, identical code block is executed by every thread. The whole thing, right? So every thread essentially runs as many times as there are a number of steps there. Okay, so I think maybe I glossed over this thing. If you look at the loop, it's different now, right? If you look at the for loops condition variable, it's not increasing, it's not I equals I plus, it's not I plus plus. It's I equals I plus num threads. Why? Because the first thread executes 1, 5, 9, and the second thread executes 2, 6, whatever. You can do it differently. You can divide the range in a consecutive way, and the first thread will execute from 0 to number of elements divided by threads. The second one will execute the rest number of threads and divided by number of threads. That might be more efficient for cache reasons, doesn't matter. But I changed the for loop explicitly myself, and in order to ensure correctness, I did put these funny if statements to make sure that I cover the corner cases. In fact, I might have made a bug here because I might have not thought about the fact that the size of the array that I'm trying to, what is this thing called? Actually, not the size. The number of steps might not be divisible by the number of threads. Maybe I didn't think about it. In fact, I probably didn't think about it, and it's wrong by a small approximation. I have to think about that fact as well to make sure that I cover the corner cases when things are not divisible. And surprise, the corner case is not the unusual case. Almost always it's not going to be divisible. Statistically speaking, if you have a large thread count, your random number of steps will not be divisible by threads. So how does OpenMP make your life easier? Instead of you managing the loop indices, you can let OpenMP deal with the loop indices, okay? So, so this is called Paragma OMP4. So what does 4 does is, this is only meaningful inside a parallel region. It says, divide this iteration space to threads. I don't care how you divide it, just divide it. Like, I want this loop to be executed n times when summed over all threads. I want every single iteration of them is executed by one thread. I don't know, you can divide it like the way I did, 0, 4, 6 to the first thread, and 1, 5, and 9 to the second thread, or you can divide it differently. But I don't want redundant computation. I want this thread to be executed, each iteration of it, once by one of the threads only. So that's what you do it with OMP4. If you didn't put OMP4, the total number of times that neat stuff will be called would be n times p. P is the number of threads. Okay? But now, the number of times the neat stuff will be called is exactly n. So that's what it is. It's a convenience function, very useful. And you'll probably use this more often than writing your own iteration space divisions. And why this is important, the motivating example is, in order to write the summation of two arrays correctly, the way you would do it by taking care of the corner cases is the one you see in the middle. Right? You say, where does my start index, where does my end index, and if things are not divisible, what should be my end index? This is the correction. For the last thread, I need to make sure that the end doesn't go beyond the array boundaries. And that's fine, this is correct. But hey, come on, this is 8 lines. You can actually do it in 1 line and OpenMP runtime will split it for you. It's probably much better, right? In fact, life gets even better than this. You can even merge these things. And I don't know if I have a slide or not, but you don't need to write it like OpenMP OMP parallel and then OpenMP OMP4. There's a shortcut for this called OpenMP Pragma OMP parallel 4, which merges these things too. But be careful. When people analyze OpenMP codes in public on GitHub, there was a research paper, not just GitHub, whatever publicly available repository, they found bugs, and one of the most common bugs is not understanding the difference between parallel 4, or parallel by itself. There were lots of instances where the codes were executing redundantly, and the thing that they were trying to compute was computing p times more, because, you know, it's such a simple thing, but somehow it was a very common bug. So how does this 4 gets divided and scheduled? There is a way to tell this. By default, there is a static division, meaning that the compiler will look at the n, the numbers of times the loop should execute, and will divide it statically. So it will do this for you directly. It's usually compile time. It will create this code for you. Fine. Well, this is okay if you're computing pi. But if you're doing something where each one of these additions take a different time, and why would that happen? In some sense, there's lots of irregular computations that if you divide the array to equal pieces, that doesn't mean you're going to get load balanced assignment of work to threads. It might be possible that f of 1 takes longer to execute than f of 2. So in those cases, you wouldn't use a static scheduling. You would say to compilers, I want something more dynamic. Instead of dividing the work in compile time statically beforehand, please do it dynamically. So basically divide the space, let's say, into lots of pieces, and if it looks like one processor is taking longer time, divide this work again. And if the other processor is not taking lots of time, don't divide it. So that's called a dynamic. And you can add a clause in the schedule. So basically what you would write is Pragma OMP4 schedule static. That's the default, you don't need to write that. But you can say Pragma OMP4 dynamic. You can find a syntax for this, and it will dynamically schedule it. Unless you have a reason to think that the loop will be load imbalance, I would caution against dynamic because it's more expensive to determine this in runtime. If you have a potential load imbalance computation, try it, it might be much faster. And there's other two that I'm not going to talk, called auto and guided. What auto does is essentially what Java compilers do. As the code runs, Java compilers sometimes actually will say, it looks like I miscompiled this initially. This part is actually taking more time. I can recompile on the fly and get a faster execution as it goes on. Auto does that. It says, hey, it looks like my schedule was bad for this loop, but I see the same loop again called. Now I'm just gonna, learn from this. Again, it's a little esoteric question.
Yeah, so is that the same as the JIT compiler?
Yeah.
Oh.
I mean, not the same. The idea is the same. The implementation, God knows how they implemented auto. It's based on the compiler. Everyone has their own runtime. Every compiler has their OpenMP runtime. And there's something called guided, which you can look it up. It's somewhat like a not so strong dynamic. It's not necessarily dynamic. It's like only do dynamic if you think it's necessary. You're telling the compiler. Not important. This is the shortcut I talked to you about. And here's the slide for that. You don't need to write 2 lines. You can write it 1 line. But that's all. These are equivalent. This is the shorthand for putting a OMP4 inside a OMP parallel region. OMP parallel 4. This is probably the most commonly used construct in all of OpenMP, by the way. All right. Here's the workflow, and I think this is important. Most of the time, when people are working with OpenMP for simple applications, what they're going to do is they're going to find the compute-intensive loop, and they're going to find out the issue with that loop. Like if the loop iterations are not independent, you cannot parallelize this thing. So look at this loop. There is a variable called j, right? Okay. and then it's incremented. So it's a loop-dependent variable. It's not that hard to convert this to make it a static thing. So you can basically change this thing and say, instead of having j as a separate thing, I'm going to make this dependent of I. So, so essentially you're removing the loop carried dependence, and then it will execute in parallel correctly. You can do this for vectorization too. You will need to tell the compiler that, you might think that this is dependent, but they're not dependent. I'm going to show you how to do that kind of issue. All right, just a recipe. Here is a commonly used construct as well called reduction. This happens a lot. You have a long array. You're trying to compute the average of the values there, right? And even there's a standard library has functions like accumulate. You accumulate the array, and then you divide the number of entries, you find the average. How do you do that? How do you accumulate an array? It's called a reduction. You can find the max, you can find the min, you can do a lot of things, but it's very commonly used. So OpenMP has a construct for this. It's an attachment to the parallel for. You basically add at the end a reduction. Literally, you write reduction. And in open parentheses, you first tell it what is the operator for the reduction is. And then basically, you're done, simply. And what is the variable you're reducing on? The average is not a keyword here. Average is a variable, AVE. So you say, what is the operator? Operator is plus. What's the variable that you're reducing on? It's the AVE, and then AVE. Is that the right pronunciation? Maybe. And you're done. So what the compiler will do under the covers, it will create probably one of the codes we have seen. It will create private copies of AVE for each thread, and it will merge them at the end using some sort of critical section. So it's basically a convenience function. It might have, the compiler might not be as good as you are, so you might lose 10% of speed up in some cases. If it matters for you, you can do it by hand. If it doesn't matter for you, this is nice. And there's lots of different reductions. Most people just use plus and multiply, but there's much more. They might be longer than this. There's lots of Boolean stuff and so on. So let's apply this to our pi loop, and what would we do? The number of lines are actually shrinking even significantly, right? So we basically are parallelizing pi with only 4 additional lines of code. Remember, the black ones were already there, and the only things that I'm adding are the red lines for parallelism. Now all I'm doing is adding the header, adding adding the parallel, and adding a reduction, right? So that's all there is. And the reduction will automatically add it to sum. And as I said, there's a little bit of extra overhead, potentially, depending on how it created. This might not be true for every version of OpenMP. The chances are the parallel for is not as efficient as it should be in this particular case. So, MP4, sorry, parallel for, same thing. So the thread creation cost is probably higher. And so you lose a little bit of performance, but you're still significantly faster than the case where you had full sharing. Any questions so far? Okay. I know that the problem with OpenMP lectures is there's a laundry list of things, and it's not really teaching you walking through an algorithm. It's more like, here are the things you should be aware of, and just keep them in the back of your mind when you're writing code. And because it's really hard to Google things that you don't know the name for, right? So this is essentially what's going to help. Here's no wait. What did I say earlier on about barriers? Barriers says, until all the threads come to the barrier, no thread exits the barrier. That's essentially the semantics. Every one of these work sharing constructs imply a barrier at the end. So when you have an OMP4, there is a barrier, whether you know it or not, by default, because that's the safe thing to do. OpenMP could have chosen not to do it, but they chose to imply an implicit barrier at the end. Well, bad news is sometimes you don't need that one. And imagine that you're using all the cores in your machine. You have 8 cores, 8 of them are running a computationally intensive loop. And at some point, an operating system interrupt comes. Someone starts watching YouTube video or something, like you open up a big file. Okay, one of the threads needs to go deal with that. He's going to get slower. But the chances are the next time an interrupt happens in the next loop, the operating system will pick a different thread. It will pick 3 as opposed to 1. Okay, now, if you synchronize at the end of every loop, even if you don't need it, the things are going to run at the pace of the slowest guy all the time. You know, that you put a, you know, this is like going to one place to the other with 80 people. And you wait for the slowest guy to synchronize at the end of that block and so on. You would have gone there much faster if you just said, hey, here's the destination, everyone gets there in the same speed. So if you don't think that there needs to be an implicit barrier, you can put this extra clause called no wait at the end of your work sharing constructs. And what it says is telling the system that, look at this thing that I'm updating, the array B. In the next line, or any other line in this code, there's no one that uses B, right? So there's no reason after this loop people need to synchronize. B is not used later. But you cannot do the same thing for the previous loop, because the previous loop is updating C, and C is used in the next loop. If I had put a no wait there, the chances are I would create an error, because there would be some updates still happening to C, which would not be seen by the next loop, and they would read garbage. They would see stale updates from the original initialization. Things would get messy. Now, for that, keeping the implicit barrier is great. For the second loop, you don't need it, so you delete it. You can basically use no wait whenever you're sure that whatever is updated inside the loop is not going to be used until the next barrier at least. It can be that it's not used for another 10 lines, and you already have a barrier before it starts getting used, then you can put no wait there. Okay, now this is the trickiest part. I'm not even sure it's easy to get it the first time. Maybe it's easy. Some people say it's too easy and people make it complicated. The most variables are shared by default. I said the default is if the variable is defined before the loop or before the parallel region, it's shared across all threads. And whatever is defined inside the parallel region is private, but you can change those. So how do you change those? Again, the example was index is shared by default, right, in this example. And everyone creates a copy of temp. What is temp? Temp is this internal array within the work function, and work function is called within the parallel region. Consecutively, every thread will create its own version of temp because it's local thread. Fine. All good. And how do I change this? If I want instead something different, if I want to say, I want every thread have a separate copy of the index variable. I don't know why. You might want it. I'll show you why, some examples where you might say. And then how would you do that? You would use these constructs within your parallel region. You will say, these variables are shared, these variables are private. And then there's this thing called first private, which I'll describe in a minute. Okay, so private basically says make a copy for each thread. So here you see in this example that I'm adding, this is just like the same summation example. I'm adding the values from 1 to 1,000. And if I didn't put this private, there's a data race, right? Everyone is updating the temp variable. That's bad. But instead what it can say is, make this private and keep adding to it. That's still wrong. This is still wrong, but it's just telling you what's going on. So why is this wrong? For many reasons it's wrong. Private creates a separate variable, but doesn't initialize it. So you're already adding to garbage. Like you're summing entries to a garbage initialization. So you're going to get some random numbers. Verse, whatever you called private is going to be destroyed before the loop, before the parallel clause exits. So the parallel clause is only affecting this for loop, and as soon as that for loop is over, those private entries will not have liveness anymore. So you will resort back to the original temp, which didn't get updated, so it will still be 0. It's wrong, but this is one way to change the semantics. So I think I said all the things that I wanted to say here. So to fix that initialization error, there is this guy called first private. What do you say is, initialize, while you're creating a private copy for each one, for this variable, for each thread, get its value from the initialization it had before it entered the loop, before it entered the parallel region. So it basically says, what was the value of increment before the parallel region started? It's 0. So it's going to have the increment private variable will have initialized value of 0. So each thread will get a copy of increment variable, and each one of it will have an initial value of 0. This sounds more useful, right? In practice. We're just giving you all. Here's a test you can do later, going over the slides, because I don't want to run out of time. But well, actually, we can do this. So what's going to happen? There are 3 variables, A, B, C. And then I start a parallel region. I say B is private, C is first private. So what's happening inside the region? What happens after the region is over? So what will happen to A inside the region is going to be shared. Everyone will have value 1, but they'll be all pointing to the same variable. Inside the region, B will not have a value. It's going to be uninitialized. Inside the region, C will have value 1, because that's the value it was before, and everyone will have a separate copy. All good. What about the exit? At the exit, B and C will revert back to the original values, 1 and 1. And A, God knows A, if I updated A inside the region, it will get reflected. So it will affect the shared variable. So I don't know because there's no code here. Here's an example. But okay, this is an important thing to know. A default says, there are a lot of defaults, like the variables that are outside the parallel region are shared. And one thing that I didn't say is, the loop indices are private by default. But the first loop, under the parallel force indices are private by default. So this 0 to n, remember this is a parallel force, this I variable will be parallel. So we will be private because it doesn't make sense any other way. Otherwise there will be a data race condition anyway. So these I variables will be private per thread. But that doesn't extend to the second loop, because this parallel for only affects the first loop, right? So what it does, the default says is, unless I specify things explicitly, do not apply defaults. Warn me and say that I forgot to specify the shared private whatnot property of some arrays. And it will complain. It will complain specifically for J, because there's a J variable here, and I did not specify what to do with it, whether it's shared or not. In fact, making J shared is almost guaranteed to be a wrong thing to do in this loop. I probably made a mistake, and the compiler will tell me that, it won't tell me I made a mistake because it doesn't have semantic information. It just will point me out to something I might have made a mistake, and I will say, oh yeah, I forgot to say that J needs to be private. And then this is your debugging tool, default none. Warn me about anything that I didn't tell. All right. Questions? Too many different constructs? Apologies in advance. But one of the feedbacks we got from this course in the last several years is, this course is great, it's heavily based on homeworks, and we were talking about conceptual parallel computing things more than programming. So here we are. Lots of programming for you. The task clause got added to OpenMP fairly late in the game. And what does that mean? That means like, this is very useful for divide and conquer computation. Imagine you're writing quicksort. How many of you know quicksort? Okay. Lots of people know quicksort. So essentially, quicksort is an algorithm where you pick in the original description, random entry called pivot from the array, and you split your array into two. All the elements that are bigger than that entry, pivot entry, and all the elements that are smaller. And then you recursively call sort on each side, unless you have done something to ensure that the pivot is the median element. And there are some variants of quicksort that does that. We'll see those later in the class. It's not necessarily going to be balanced, right? On average, it's going to be okay. But if you're calling some in parallel, say, this looks like very easy to write in parallel using task. You say, I'm going to create a task for the quicksort recursive call I made, and a separate call for the other. So, and then it will just continue creating recursive calls. So tasks are very useful for those cases. The algorithms that are harder to describe as loops, but much more natural when there are recursive calls. The pictures are probably not useful here. I'm going to actually start with this and go backwards. First, give you the motivation of why this is happening. Let's say you're calculating Fibonacci numbers, right? You have seen in algorithms class that you should not calculate Fibonacci numbers recursively. I know, but I will still tell it recursively because it illustrates tasks. The definition of Fibonacci number is f of n equals f of n minus 1 plus f of n minus 2, right? And I don't care about math for this particular case, and I stupidly write a code that calculates this recursively. And it's taking too much time, and I think I can parallelize this to, I have 16 cores. I can do something useful. What do? I will create a task to compute each one of these recursive calls. In the original time that I learned this, there was a language called Silk, which you can Google it. There's still a language called Silk. It made this thing so much easier. The syntax were like, every time you had a recursive call, you would say spawn a new task. And then it will go spawn a task. That was the syntax. All you would change here was Silk spawn before you call x equals Fibonacci n minus 1. And the original calling thread will compute the Fibonacci n minus 2. You wouldn't put a spawn for that guy. It would be the continuation. So that's the same idea, except in OpenMP, syntax is a little hairier because of the way they design tasks. It's a decision choice. In fact, it looks like this. You create there is no continuation in some sense. You say, hey, I want to create a task, but I want to say that the value that's assigned from the task should be shared. Like you say shared x. If you don't say shared x, the x will not be visible outside the task. But you need that because you're going to use it to sum x and y. And then you create a task with shared y, and then boom, and then you say, wait for these tasks to compute and finish. That's important because you're going to get otherwise unfinished computation and probably incorrect x. Task wait says, wait until all the tasks that are created above this finishes. And once that finishes, I know that x and y are the correct values, and I will sum them up and return this. Magically, the same thing is happening in the recursive calls to Fibonacci. More and more tasks are created like this in the loop, and then basically it creates some sort of tree like this. Things are getting created, and then they get joined, and it will be usually nicely load balanced depending on what good scheduler OpenMP runtime is using. Most of us don't know exact scheduling was using, but it's fairly okay. So I gave you the idea, hopefully. Now the syntax. Now I'll go back and tell you about the syntax. Is the motivation making sense at least? Okay. All right, so there's a construct called single. This is different than critical. Remember, critical is a synchronization construct. It's like a mutex. Single is a work sharing construct, and it tells you not to share work. It says only one thread will ever execute this line. It doesn't say only one thread executes at a time. It says ever. This part of the code should be executed once. So that's fine. What is it? What does this have to do with the tasks? this usually is the way people use tasks. Right, so they will create a single region inside a parallel saying that only one thread should execute this big block, and then within that region they will create tasks. To me it's like this, like, you know, you first create a parallel region and then you create a single region and then you create tasks. Does it make sense to you? I'm sorry this is recorded, but normally in a sane language you would put neither one of these, parallel or single. You would just say OMP task, run this thing, OMP task, run this thing, and wait and done. Unfortunately, what does OpenMP says is unless you put these things inside an OMP parallel region, nothing is parallel. For that reason, you have to put an OMP parallel. And once you put an OMP parallel, now it will be duplicated by each processor. Everyone will run it, but you don't want that either. So you put parallel, and then you put single, and then you put tasks. It's just syntax. Maybe in the next iteration they'll create a shortcut, just like they created a parallel for shortcut. But this is currently the commonly used way of doing it. It doesn't have any performance bottlenecks just because the syntax is ugly. It's just ugly. And then this will create tasks for Fred, Daisy, and Billy. All the functions. I told already about the task wait. You can put it before. There is a task wait implicitly at the end of that single construct, whatever the first work sharing construct is outside the task region. It will be the end of this line here. But if you want to wait before, let's say Billy depends on some result of Fred and Daisy, and you want to make sure that Fred and Daisy have completed before you call Billy, you can just insert a task wait here. That's fine. And then there's this thing about all these shared variables, right? So the same concepts usually apply, and it's not that complicated. So usually what you want in tasks is first private, but you can read the spec to see if you need something more special. More often than not, the default, I believe in this case, is first private, and if you want it to be different, you will say it, right? So you'll say, okay, I want A to be shared, and you'll, just like the other cases, you will put it inside the parallel region, make A shared, and so on. One caveat that makes life complicated here is this. If you declare something private, just like in this example, right, outside the task call, the having a task call will automatically convert it to be a first private. That's what it is. Because they think this is the safe way to do it, and this should be the correct way, so they will silently fix your intentions. Okay? Just know that. And we already saw Fibonacci numbers. We have practically no time left. And I never intended to finish the rest of this. You can read those. There's two important things you might worry about. One is flush, and one is atomic. They're in the slides. And you can go to the nurse class as well. So what does flush do? Let me actually say, forget about atomic. Flush is something that provides a consistent view of the memory. I read the slide, I know, but it's actually important. Nothing guarantees. Here's the example. Okay, let's say you have two threads. This blue little example I'm showing is the most useful thing. Okay, so thread 1 sets x to 1, thread 2, and then sets y to 1. And then thread 2 reads y, and then reads x. You might think as a sane person, not caring about the details about compilers, says if thread 2 is successfully reading a value of 1 from y, it can assume that x is also 1. Thread 2. Thread 2, if it sees R1 to be 1, since the instruction x equals 1 comes before y equals 1 in the first thread, the one programmer can think that if y is 1, x is already 1, because the call to x equals 1 comes before that. Is that correct? It's actually not. This is the problem. The compiler doesn't see parallelism. The compiler will compile thread 1 separately from thread 2. And the compiler will say, there's x equals 1, there's y equals 1. Well, they're not dependent on each other, they're just setting different variables. I can just reorder these things. It will reorder this thing. It's fine. I'm not saying it will do it, it might. And then in which case, thread 2, even though it sees value 1 in y, the x might be still undefined, or the previous entry. So that kind of reasoning about the other thread is not exactly generally correct. So the way you would enforce it is something called a flush, meaning that you put a flush in between x equals 1 and y equals 1, and what we'll say is all the updates to the memory locations before the flush statements needs to be visible to the other threads. That's the effect. So you would get the correct behavior that way.
How is this different from barrier for thread 1?
The barrier will just ensure the execution comes to that point. Thread 1 will indeed execute x equals 1 if you put a barrier, but it will not guarantee that the value is visible to the other thread. It will not propagate the value to the threads. This is a memory operation. Barrier is just a, where did the code come to kind of problem. So that was the only important thing I wanted to finish up with. In summary, what's the takeaway? Programming shared memory is both easy and hard. Why is it easy? It takes less investment initially to convert a serial program to a shared memory parallel program than it is for distributed memory. You can just put a bunch of pragmas here and there, and you will get initially parallel code. The downside is harder to think about. If you were using message passing, the chances are you would never create data races. But here, it's very easy to create synchronization bugs, so you have to be a little more careful and think a little harder. And the pthreads does not make your life easy for this kind of reasoning, so that's why we have concurrency platforms like Silk, OpenMP, TBB, whatnot. And here's a bunch of other options that you can look at, but for this class, we'll be using OpenMP. And if you want to learn more about OpenMP, there's a tutorial that's linked from the website. It might be useful for the rest of your life, or at least in your project if you decide to use OpenMP for your project. That's all. Thank you.